We've heard it so many times, electricity and water don't mix. I'm here today because I have a question. Are electric boats safe for us to use in the water? So to find out, I'm here in San Francisco, California at Stoffel Systems. They manufacture high voltage battery packs for vehicles. We're going to look inside a battery pack and see the architecture, to see the safety measures they put inside these packs and make a determination if they're really safe or not.
All right, so let's give you a tour here of Stoffel Systems. Any good engineering office has a fully stocked kitchen to keep everyone happy. Very important. I'm Eric Stoffel, president and founder of Stoffel Systems. I'm an electrical engineer by training. I started this company in 2010 as a solo consultant and grew it to what it is today. We're a leading provider of non-automotive battery systems, so basically everything off-highway.
So what does Eric think about our question as to whether or not electric boats are safe?
Electric boats are definitely a safe and performant option. The concerns about safety are kind of discomfort around electricity and water, but with proper engineering, you can have a really nicely sealed battery pack that has no exposed conductors or electricity, such that there's just no exposure to the environment in general. So again, a properly designed electric vehicle powertrain system is fully IP67 sealed, which means that it can get fully submerged with no issues at all. So again, properly engineered, an electric boat is absolutely safe and a great option, and something that I think we'll see a lot more in the future.
Eric is going to give us a tour of their factory and show us all of the rigorous testing that goes into making a pack safe for the water. But first, let's take a look at the components inside a high voltage marine battery pack. A battery starts with a cell. This is where the energy is actually stored inside the pack, and in our example, they're using pouch cells. The cells are then combined into a 3D printed skeleton and connected to something called a BMS, or battery management system, into a block that they call a module. The modules are then placed on top of cooling plates and placed inside a steel case and connected in series and parallel. Coolant lines are then placed inside the battery pack and connected to the cooling plates. Lastly, everything is connected to a PDU, or power distribution unit. This contains fuses and the master BMS, which communicates with the controller and allows the power to be released from the pack. It seems relatively simple, but there is so much going on inside this pack to keep it safe from fire and electrocution.
Over here we have what we call our high pot system, or high potential testing. So we can to test the isolation, electrical isolation between your high voltage domain and low voltage domain. One of the things for shock safety that's very important is that the battery cells themselves are electrically insulated from the case. So you never want to have your negative terminal or positive terminal or any interstitial terminals electrically connected to the case for shock safety. So one of the ways you check that is to make sure you have excellent isolation resistance and high potential withstand voltage between your high voltage domain and low voltage domain. So what we do is we basically, in a test, we apply 5,000 volts or up to 12,000 volts between the center of the battery pack, the electrical connections, and the outside of the battery pack, and ensure that all our electrical insulating layers are functioning as expected. And there's a huge amount of overage on that because our battery packs are typically 400 volts or 800 volts. And if we're testing at 5 kilovolts, that's about 5-6 times higher voltage than it needs to be. But you need to do that for the capability of the isolation barrier. So the isolation barrier is something that you want to monitor over the health of the battery as well. So we actually have some patented technology that does that for us. It's called vectored isolation monitoring. And what that does is it basically measures the resistance between your high voltage domain and your low voltage domain. And it tells you not only what the magnitude of your resistance of the isolation fault is, but where in the electrical stack it is, and also what the Y capacitance contribution is. So that allows you to assess what the total available shock risk is. And what happens over time is if that resistance starts going down, then you can tell that you're having a breakdown of your isolation, and then you'd want to take the pack offline such that it doesn't create a shock hazard to the user. Over here we have some battery packs in the different states of assembly. So we're actually putting together these high voltage battery packs. This is what it looks like when the battery pack is completed. This is the face that has all the connections to the rest of the system. So for example, this is a coolant inlet. So cold coolant would come in here. It would distribute within the pack through these cold plates and then cool the cells so they don't get too hot during operation or charge. And then you pull out the warmer coolant here and put it through a radiator and a pump. Here, this is a high voltage connector. This is a shielded high voltage connector with something called HVIL, or high voltage interlock. What that allows you to do is it detects if the connector is present. So That way, if for any reason the connector becomes disconnected, there's no way for the system to close contactors such that there's no voltage ever exposed at these terminals if it's disconnected. This is the low voltage power and communication interface to the rest of the system. So typically 12 volts is coming in here and it's communicating via something like CAN bus or Ethernet to the rest of the system, and it has some discrete I/O as well. And that allows you to handshake with the vehicle controller or the vessel controller and then turn on the battery pack and make sure that everything is safe to go before you connect power. Finally, we have some lights here just for operator knowledge about how the battery pack's performing. So then this is what it looks like internally. Obviously, this battery pack is in a state of partial assembly, but this shows different modules connected in electrical series connection such that we build up the voltage and thus power of the system that we're trying to power. So this is a 400-volt battery pack that's actually being used in a jet ski application. So cooling is very important, especially for high power applications. So in the marine environment, high power is kind of the name of the game because you have a lot of water you're pushing out of the way. And so you want to make sure that your battery pack doesn't overheat so that you don't have to reduce your current draw just to help it cool down. So by having great cooling management, you can keep your battery pack in the ideal temperature and operate it as long as the state of charge will allow. Okay. One thing that's actually really nice about the marine environment is you have an infinite thermal reservoir with the water. So basically, you can have a heat exchanger with either lake or seawater that then exchanges it with a coolant such that you get between 15 degrees C and 30 degrees C water, and then you can basically evacuate as much heat as you want out of that.
Do you guys see a difference between, let's say, an automotive battery and a marine battery as far as the power discharge?
That's a great question. So yes, because a marine battery, generally speaking, when you're up to speed, you're pulling pretty much full power because you're pushing a lot of water. So you're pulling a lot more power than on an electric vehicle, because electric vehicle, you basically are pulling a lot of power when you're accelerating, but when you're cruising, your power level is not as high. So electric vehicle batteries actually are not that power dense. They're mainly energy packs. But for marine, especially high performance marine, you do have some power demands on it that are in excess of what would typically be seen in an electric vehicle pack. That being said, if you have a very, very large marine pack, then the power level comes down, relatively speaking. So it kind of depends on the vessel and what the power level of the vessel is. All right, over here is our high voltage test area and cell testing area. So we have a number of environmental chambers that we test the battery cells at different temperatures and humidity levels, and then we can run it at different charge and discharge rates. So one of the things that's very important for us is developing what we call state of charge and state of health accuracy algorithms. And what that allows us to do is estimate the state of charge of a battery pack, which is basically the fuel gauge, how much energy you have remaining, and state of health, because one of the things that's interesting about battery packs is over time, the amount of energy they can store typically goes down. So, a fresh battery pack can store 100% of the energy at the beginning of life, and then maybe after 1,000 cycles, you're down to 90% beginning of life capacity. So we need to estimate that very accurately so that a user always is very confident that when the battery pack fuel gauge says you have 40% remaining, you truly have 40% remaining. And it's not like one of those phone things where, it says 20% and then 1 minute later it's the phone shutting off. Unfortunately, we all have that experience. It's because of bad SOC estimation.
What do you find that humidity does to a cell over time?
Yeah, that's a great question. So humidity is really more, we actually typically use humidity testing more for like module level testing, because humidity, we want to make sure that when the humidity cycling is going up and down, you can get condensation. And we basically test that we have a good conformal coating layer and application such that we don't have any undesired conductivity between adjacent conductors that is caused by the humidity. So the humidity itself typically doesn't affect the performance of the cell directly, but it affects the performance of the overall module in terms of long-term safety.
So in different temperature environments, you might get some moisture in the pack. But
exactly.
It's probably inevitable.
Yeah, so you're going to get moisture in the pack because you need to have a Gore breather, and the Gore breather doesn't allow liquid water to go through, but allows water vapor to go through. Mm-hmm. And so one of the ways we solve that is with a desiccant package within the pack that helps absorb a bunch of that moisture and keeps the humidity levels within the pack lower, such that the probability of condensation is much less. And even if there is condensation, we use a lot of potting and conformal coating and other coverage methods to prevent the condensation from ever affecting the safety of the battery pack. So over here, we're doing some ESD testing. This is basically electrostatic discharge. We're basically taking an ESD gun. You can see what this is. This generates a lot of static electricity to the same way that walking across a dry carpet would.
So don't touch the end of it.
So don't touch the end, especially when it's powered, but it can generate sparks about that big. And so we zap the boards to make sure that, and the electronics, that they work even in an environment where sometimes you get electrostatic discharge. This is a battery module under test, basically seeing how it performs thermally. We use a variety of different cyclers here. We have a module level cycler that's grid interactive, which means it charges and discharges actively to the grid. And then we have a 1,000 volt, 60 kilowatt bidirectional supply, so we can charge and discharge from the grid up to 1,000 volts with this piece of equipment.
How many cycles will you run the battery through?
Great question. It depends on what we're doing. In this case, we're looking at thermal characterization, so we're going to be probably running about 6 to 12 different tests at different charge and discharge rates. But then for cycle life testing, we would do more like 1,000 cycles or 2,000 cycles, so charge it up and down a bunch of times. Yep. This is a coolant preconditioner. So what this does is it allows us to set a coolant temperature and coolant flow rate, so we can simulate our liquid cooled batteries and cold plates to see how they actually would perform in a liquid cooling scenario. Yes, so liquid cooled batteries perform a lot better than non-liquid cooled batteries because liquid cooling allows you to really get that heat out. So for example, a battery pack that is not liquid cooled, you might be able to discharge it what's called a 1C rate, which means you can discharge it at the full pack in an hour. But a pack with liquid cooling could let you get as high as a 5C rate or a 4C rate, which means that you're discharging the entire pack in about 12 or 15 minutes. We actually have a full UN383 test lab. So what does that mean? Battery packs, in order to be able to ship them, particularly by air, you have to test them to make sure they're safe in abuse conditions. So UN383 is an international standard for shipping battery packs via air. So we have what's called T1 through T7 here. Those are the different tests you perform. T1 is an altitude test. So basically we simulate the battery packs at 60,000 feet equivalent altitude to simulate
this is basically like a vacuum chamber.
This is a vacuum chamber, exactly. So we can simulate basically what happens when a battery's on an aircraft and it goes decompression. So that's what this is simulating. This is a shock tester. So what we do is we basically take a battery module and we put it on here and we drop it from different heights onto different discs that basically create a different half-sine pulse that essentially shocks the battery. We usually do it in different orientations to simulate drops and shocks and that sort of thing. So this is very important for the marine industry because every time the boat is hitting a wave, we want to make sure that the battery pack is not going to get damaged by that. So we typically test up to 50 to 150 Gs of shock. Typically it's like a 6 millisecond sine wave pulse. Here, this is a vibration tester. So what this does is allows us to take a battery module or board or unit, kind of anything we can test, and we can run a frequency sweep. So basically we can set different Gs we want to test at different frequencies to see if there's any resonant patterns or vibratory modes where something could get damaged. So for example, what we're looking at here is you can actually have, this is a transient test, so you can actually see the vibration and the acceleration at different times, but we can also run frequency sweeps where basically you start out at 20 hertz, go to 1000 hertz, and run different G magnitudes of amplitude to test that out. One thing that's funny about this is sometimes when you get a certain frequency that resonates with the building, the whole building starts to shake.
Like a musical instrument or something.
Exactly, yeah.
Based on your testing, the shock testing and the vibration, what have you had to do to the pack structure to, I guess, mitigate those?
Yeah, there's a lot of learning from that. It's one of the things you can't just simulate. You really have to test and learn from. So it's really helped us to come up with good ways of capturing cells so that you never want to have a cell that's kind of loose within a battery pack because then it can kind of jiggle around and get damaged. So we think about foams, we think about potting, we think about RTVs, different kind of compliant mediums that allow you to capture the cell with some flexibility such that the shock and vibration don't create actual damage to like a collector plate or a cell tab or something like that.
Yeah, it's so important, especially in a marine environment on a fast boat where you're just getting so many impacts.
Exactly. Yeah. So that's very important. We find that testing is critical, especially for the marine environment. This is a CNC conformal coating machine. So basically what we do is we can apply a clear coat conformal coating to all our boards such that they will perform better in humid or contaminated conditions. So this is very important for marine because it helps prevent contamination, increases device lifetime.
So given all the monitoring and testing to keep these batteries safe, I still had to ask, what happens if there's a fire and your boat sinks? Will you get shocked?
If in the rare chance a battery pack catches fire in a boat, the question is, do you have a shock risk? And the chances of being electrocuted or shocked with a high voltage battery pack in the water are very, very low. And here's why. So most people think electricity is just something that's out there that you touch and you can get shocked. In reality, electricity always flows in circuits, which means it has to go from typically a positive terminal to a negative terminal if it's DC. And so the issue is with a battery pack, or the reason it's more safe is because a battery pack has all the current self-contained. So basically you have a positive and negative terminal, but the chances that it's actually going to flow the current all the way outside through the water, through the person and back is very, very low. You'd have to be touching it just in the wrong way to have that happen. In reality, what most likely would occur is the current would flow just in a very short loop within the salt water itself, because salt water is conductive, or even in lake water, fresh water is still partially conductive. It is very, very rare that you would actually have a shock risk from a battery pack in a boat that's properly engineered. The other thing to note is that the battery pack, if it catches fire, what is the number one thing firefighters do with an electric vehicle battery? They flood it with water. So you're already in the water, and that would help cool the battery pack to prevent additional thermal runaway from cascading. So typically the way that a battery pack would fail and catch fire is one or more cells would actually go into what's called thermal runaway, which means it's generating a lot of heat, some fire, some explosion, but that's usually a small fraction of the pack. In order to have a absolute worst case scenario, you need the whole pack to go into thermal runaway. But if you're in a water environment and the boat's sinking or something like that, you have a lot of thermal mass caused by the water that would actually prevent some of that propagation from occurring. So it's very unlikely that you would have what I'd call a true catastrophic failure. But again, it takes proper engineering discipline and principles to be able to make sure that the system is safe and would not cascade into a failure like that.
So there we have it. There are risks, but given a properly engineered battery pack, electric boating can be very safe. Big thank you to everybody at Stoffel Systems for letting us in their facility and teaching us about high voltage pack safety. I'm Justin with Aqua Electric. Thanks for watching.